tagadan 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 pam pam tagadan 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 pam pam tagadan 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 pam pam tagadan.
All right, our next presentation comes from ETH, from Maciej Besta and Niels Block. Gentlemen, how are you today?
We're good, thanks. How about you guys?
Fantastic. We're going to be talking about SlimFly.
Yes, and not only SlimFly, but mostly SlimFly. Okay, so let me share my screen now. Hold on a second. You should now see the slides. Can you confirm?
They're loading in right now.
Okay, so can you confirm that you can see the presentation?
Perfect. See it now.
Yes, wonderful. Okay, so let's start. Welcome. I'm Maciej. I'm a researcher from ETH Zurich, from SPCL lab at ETH Zurich, led by Thorsten Heffler. And today, together with Niels, who was also on this project, we're going to present our recent progress into the effort of developing high-performance interconnects based on InfiniBand architectures using the underlying SlimFly topologies, in collaboration with CSCS and with Hussein Harake. That was key for this effort. Okay, so as we all know, interconnects are very important elements of large-scale compute centers, accounting for large parts of cost and power consumption. As we know, for example, data centers or like the interconnects in data centers can consume as much as half of the power consumption of the total infrastructure, and they can be even 1/3 of the total construction cost. So we'd like to somewhat minimize these things when building a network. But the question is, how do we connect what topology of connections do we select for our equipment, for our routers, our endpoints, and then how do we route this thing? In this talk, I'm going to touch on all of these aspects. The setting we are going to speak about is the setting where you have some number of routers. All of them are connected to the same number of servers. And then these routers are connected with some router-to-router link that form the topology. In part one of the talk, we are going to speak about the topology itself. So what is the way that we connect the routers and why we are doing this in this way? In part two, we are going to take a look at how do we route over this topology. And part three, we are going to take a look at how do we then grab the topology and the routing and use it in the InfiniBand setting. So what we are proposing to do, we are proposing to connect the routers with the SlimFly topology, an efficient low diameter network topology, with the key idea, where the key idea is as follows. So in SlimFly, the key idea is to lower the diameter of the topology and thus the average path length. Why do we do this? Or let's say, what do we do first? So we have some topology, we have some routers and endpoints that are connected with some wires. And now in this particular example, these two guys that we are now marking with the red color, they need 3 hops to communicate, right? So we have the diameter of our topology is 3 because we need to cover 3 inter-router hops. And now what we propose to do is to somewhat change the structure so that we are decreasing the number of routers, at the same time increasing the endpoint density at the remaining ones to cover up for the missing endpoints, and then rewiring the whole thing so that we have lower diameter. Now these 2 endpoints need only 2 interhops to communicate, right? So we can see this hop 1, hop 2, which means we have lower diameter. But why do we want to have lower diameter? Well, we want to have the lower diameter because it gives us, on one hand, intuitively, we have fewer hops, so lower latency, so more performance. That's clear. But then what is also slightly less intuitive is that we also have less cost and less consumed power. Because as we saw, we are trying to use higher density, higher radix routers, which means that for a fixed size, we are going to have fewer routers, and thus we are going to have fewer resources needed, so less cost for constructing the thing, and also less consumed power because we have now fewer hops between endpoints, so our packet will traverse fewer buffers, right? So all these things should be now very nicely satisfied in this particular topology. Now the question is, how do we really achieve this, right? So I shown you this very fuzzily looking picture that, yeah, we kind of rewire this thing, but how do we exactly do this? So the key method for achieving this is to use the so-called Moore-bound optimization. So the Moore-bound is a very interesting notion from graph theory. It's the upper bound. So if we take a fixed graph with some input, the input radix k in our setting, it translates to number of ports in switches. The number of vertices translates to number of switches or routers. And the diameter d is, well, our diameter d. the maximum distance in the network. For these two fixed parameters, with the Moore-bound optimization, we are able to get as close to the upper bound as possible. So for these two parameters, for the fixed diameter and for a fixed port count, there is only as many routers as we can have in a given topology. And with the Moore-bound, we are getting as close as possible to this number. Right, so let's take a look at this Moore-bound in more detail. We grab one example router or switch in our topology. This adds 1 to the Moore-bound expression. Now we are grabbing the neighbors of the switch. This will add k to the Moore-bound because we have k, I mean, the degree is k, so each switch has k links to other routers or switches. And then we are adding the neighbors of the neighbors. So we are adding these terms and we are adding these terms and so on and so on. And we can do this only as many times as we have, as there's the diameter of our topology. Right? So we are summing all these terms. And this whole sum is this upper bound, right? So this is kind of can be seen that we can't really have more switches in the topology than this number. So the approach is that we fix the diameter. So to build some concrete topology, we are fixing diameter to be some low value, for example, 2, because we want to have lower latency and then this low cost. So fewer resources, low diameter. Then we fix the radix so that we are matching what our switches give us, right? So, I mean, we have only some technological constraints. We have only some number of switches that can have some limited number of ports, like 40 or 64. So we are grabbing this number. And for these two parameters, with the Moore-bound optimization, we are getting as many switches as possible. So we are minimizing cost per switch or per router, depending on what naming we are using. Right, so let's see an example SlimFly, right? So we speak a lot about how we build this. Let's see an example. So an example SlimFly that has diameter 2 and with 40 routers and 200 servers servers we are omitting from the picture, looks as follows. So these are our routers, and they are forming some groups that have the same wiring pattern in two parts of the topology. So half of the routers are forming groups with one pattern, and half of the routers are forming groups with a different pattern. And we are grouping this identical pattern groups on left and on the right side. So there are no connections, no cables between routers of the same intra-wiring type, but there is a lot of connections across this partition, right? So we have these groups, and now they are across this division, they are connected very, very densely. So these groups actually form a fully connected bipartite graph. So now I will really skip the details on how to construct this mathematically. So this is not very difficult. It all requires all this is needed is finding a special thing called a certain finite field. So we have some input parameter that we feed into our construction scheme. It just generates a simple field, like a set with some elements, and then you are just applying some equations to these elements to get the specific connections between each pairs of routers. That's not very difficult to really use in practice because we already have running SlimFly based on that scheme. I'm going to skip that because it's like a bit more time consuming, but let's take a look at something more interesting. Let's take a look at the comparison to optimality. Right? We speak a lot about this Moore bound, which is really the upper bound, and let's see how close we are to this upper bound in terms of this cost performance trade-off. So on this plot, we are plotting different data series correspond to different topologies with diameter 2. On the x-axis, we can see the network radix, so how many ports our switches have. We are scaling this, so we are increasing the size of our topology towards the right. On the y-axis, we can see the number of routers in the topology, so the larger the network is. And again, data series are different topologies. Except for this upper line, so the line at the top is the upper bound, this is the Moore bound. And now we can see that SlimFly, which is this blue data series, is very, very close to this upper bound. So we are really, really not far away from the maximum that we can get in terms of this optimality. Then the second best was flattened butterfly with diameter 2. And then there were some other topologies that were having even more far away from this optimum. Right, so this is how close we are mathematically speaking. And now let's take a look at something more like real life. So let's take a look at some results that show us the performance and the actual construction cost. So in this comparison, what we did, we compared SlimFly to both different low radix topologies, such as torus networks, or to hypercubes, or to the long hop topologies, as well as to some high radix designs, such as fat trees, flattened butterflies, dragonflies, or random topologies. And so we use a wide comparison spectrum of different designs and some example data. Here we are using cycle accurate simulations, and we are, for this particular slide, I'm showing you the results for the random uniform traffic pattern. So in this traffic pattern, every endpoint communicates with one randomly selected endpoint somewhere in the topology. Right? So we do this random selection. That's our traffic pattern, and then we have the results. So this is a slightly complicated looking plot. Let me explain. On the x-axis, you can see the offered load. So this is the fraction of the bandwidth of our uplink channels that are feeding the traffic into the topology. So the maximum is 1, the lowest value is 0. On the y-axis, we can see the latency in cycles, so our simulation latency. And then different data series correspond to different routing protocols. Most of them come from SlimFly. So we are using different proposed routing, very simple schemes for SlimFly. And then we also compare to some established protocols for Dragonfly and for Fetch Tree. So here we are increasing the load, right? So on the left part, we are kind of showing the latency results. On the right part, we are showing more the bandwidth that we are offering. And on the left side, we can see that SlimFly has the lowest latency. This is the direct consequence of having the lowest diameter. So we have like fewest hops to traverse, so of course latency is the lowest. On the right side, we can see that the bandwidth that we are offering is also very high. It's only slightly lower than that of the full non-blocking Fetch Tree, which is like really the best you can get, and it's higher than that of Dragonfly. So yes, we do have good outcomes here. And now for the construction cost. Here we have a very extensive evaluation for this in the paper. So we have lots of different models that are assuming different ways we can lay out these racks and the routers and the endpoints, different ways to connect them, different types of equipment. Here I'm just showing some example results for Mellanox stuff. On the x-axis, you can see the number of endpoints in thousands. So we are increasing the size of the topology. On the y-axis, you can see the total cost of construction, the given network, counted in millions of dollars. And again, data series correspond to different topologies. Right? And what you can see is that SlimFly is consistently the most cost-effective as a direct consequence of the fact that we have lower diameter, which means we also have smallest number of equipment that we need to use for a given traffic pattern, for a given performance to be achieved. Okay, so there's SlimFly, the low diameter topology, but there are also other topologies like that proposed over the years, most of them after SlimFly. So there's Dragonfly with diameter 2, there's HyperX with diameter 3, both with diameter 3. There's Jellyfish, and there's also the slightly more recent topology called Expander. And now the question that we also asked later after constructing SlimFly was how can we route these topologies efficiently to get most performance? So I shown you some results in performance, but they are like really simple, like technology agnostic simulations. And the question was really, how do we route this in some concrete setting? For example, assuming some Ethernet or InfiniBand. And this, we also did some follow-up work on that. But let's start with really how do we route in Fetch Trees. So there is one particular mechanism we wanted to enable in SlimFly and in these other topologies in terms of routing that is really like an important factor when it comes to achieving high performance. So in Fetch Trees, what we are doing when we are routing, you are easily using the fact that we have numerous same length shortest paths between different endpoints and routers, and this means you can easily use multipathing. Right? So we have, for example, some Fetch Tree, and for example, this guy on the left, this router on the left, wants to send these packets to the router on the right. What it can do, as we can see, it can use these two shortest paths that have the same lengths. We can achieve this by just using different core routers. So that's a very simple and a very powerful mechanism. And this mechanism is the basis for a lot of different designs on how to route in Fetch Trees with high performance. It can be, for example, this is the basis of the ECMP mechanism, but also and then of many other more complex, more involved architectures proposed over the years that target specifically Fetch Trees. And the question we asked was really, can we have something like this, some form of multipathing in SlimFly and these other low diameter networks? But first, before we go into how to actually do this in SlimFly and others, let's see what are the problems that we really want to tackle with multipathing. Because I mean, the question might be, okay, why do we even need this multipathing, right? Maybe you just need one single path. Well, the motivation is as follows. We have some network, we have some part of the topology, some routers, some endpoints. And the problem is that we may have something called flow collisions. Right? So, for example, we have some communication pattern, we have some processes talking to each other, and now depending on how we map them to the topology, there may be some problems. Right? So if we have some pair that we map this way, that we have some two endpoints talking to each other in this way, there is like one flow per path. This is very nice. But then what may happen is that if we end up with mapping which is different, if we end up with mapping, for example, two pairs of endpoints sitting on the same pair of routers, which is not really that unusual, we may have something that we call flow collision. So of course, as we can see, we now have to share the bandwidth of this path across these two pairs, so we are suffering performance loss. And this may get even more crazy because we may have, for example, like three pairs mapped to the same pair, again, even less bandwidth. And this then gets even more complex. So there are some other more complicated effects that are even more crazy than flow collisions, and we describe all these things in the paper. But what is important is that for all of these problems, multipathing would help. Right? So in this particular case, if we now route across using different paths, these flows using different paths, then we basically again have the full bandwidth of the communication. So this is what we want to achieve. So yes, multipathing would help, but now the question is, okay, now we see the problem, right? This is this flow collision that we are mapping pairs of endpoints to the same pairs of routers, and we are having to share the bandwidth. So we need to reroute using multiple paths somewhere across. But the question is, okay, for different workloads, how many of these paths do we actually need to accommodate these collision flows, right? So we know, depending on the workload, we may have different mappings, and for different workloads, these mappings may be more and less effective, and we need to have we want to have some upper bound, some number that will tell us, okay, for most of the workloads, you will have that many alternative paths to cover for all these collisions. That's what we did in our evaluation. This is like in the part 1. In part 2, we had the question, okay, once we know this number, do we have enough of these multiple paths and SlimFly and these other topologies? And then how do we actually devise routing using these insights? That's what we worked on for quite a while. And for the number of paths, I'm going to skip the details because this is like, again, it would take too much time. Details are in the paper. We did an analysis for different workloads, adversarial ones, and also like more gentle ones, trying to analyze what's the number of paths that we need, like fully disjoint alternative paths that we need to accommodate these collision flows in these workloads. And the question is, and the answer is 3. We need exactly 3 disjoint paths per router pair to handle almost all, namely more 99% of colliding flows for a large number of traffic patterns. It's a very robust insight. It's really valid for different topologies as well. So we can also use this insight for things like Expander, Dragonfly, etc., etc. And now the question is, do we have that many paths in these low diameter topologies? Right, so for this, let's take a look at this plots here. So this looks a bit complex. Let me explain. Each of these small plots corresponds to a specific topology. We have fetch trees for comparison, and we have all the others on the right. And each of these plots is a small histogram. So, so on the x-axis, there is the number of shortest paths. So remember, we still speak about shortest paths of same length, shortest paths between a router pair. And on the y-axis is the percentage of router pairs that are connected with that many shortest paths. Right? So what we can, and all these topologies come with the same construction cost, same size. What we can see on the left is that fetch tree is kind of confirming our intuition, our knowledge of this topology, right? So we can see that the 100% of pairs of routers are connected with more than 3 shortest paths, which are fully disjoint. Right? This is kind of clear. So we have these core routers. We can route through these core routers using same length shortest paths. Very symmetrical design. But we can see that this is no longer the case for low diameter networks. So depending on which one we speak about, some of them like Expander have some number of router pairs, but usually less than 50% that are connected with 3 or more disjoint shortest paths. But the lowest diameter designs like SlimFly or HyperX, they really come with almost no such pairs that are connected with that many shortest paths. So for example, for SlimFly, most of the pairs, and the same for HyperX, are connected with only 2, at most 2, disjoint shortest paths. So that's bad because we need at least 3, right? So this is kind of not really magic. So then what we did was trying to analyze, do we still have some other path diversity? So as we can't really count on shortest paths that come in these topologies, how about non-shortest paths? We also analyzed, so in the next step, we also analyzed the number of non-shortest paths that are connecting these different endpoints. So we have now a bit more complex looking plot. So let's maybe focus the attention only on this one part here on the SlimFly. So each of this, so again, we are seeing histograms here. Each row of this whole table corresponds to a specific topology like SlimFly here. Each column now corresponds to the length of the almost shortest path, right? So this, now we are speaking about paths which are not shortest, but not shortest may mean shortest plus 1, shortest plus 2, shortest plus 3 hops. So this is one more parameter that we are now counting here, and this is why we have more complex data, right? So for SlimFly, we are now seeing these 3 histograms, almost shortest paths. Okay, so we have shortest paths at 2 hops, and then almost shortest paths at 3 hops and at 4 hops. And again, in the x-axis, we can have the number of these paths that are connecting a router pair, and the y-axis is again the fraction of these pairs connected with that many non-shortest paths. And you can see that if we only increase the length of these paths that we are considering from the shortest to shortest plus 1, we already cover basically all of the router pairs with that many fully disjoint non-minimal paths. And this is even more extreme, like beneficial for us at 4 hops. At 4 hops, like 100% of the router pairs are connected with non-shortest paths that amount to 30. So 30 different paths between different router pairs. Right? So this is a very large number. And this means that we do have this diversity for paths that are almost shortest. But then the question is, how do we use these paths in the routing architecture? So yes, the key insight is that in all these topologies, actually there's enough path diversity of almost minimal paths to accommodate these flow collisions. So let's sum up. In part one, in our research of this routing part, we need 3 disjoint paths per router pair. We have this diversity when we consider almost shortest paths, namely shortest paths length +1. Then the question is how to use this in practice in routing. So we did the whole architecture for this, like the design architecture, and the key part is the routing protocol called layered routing. So what we do, how do we now use this multiple paths that are non-shortest in the routing protocol? So we have our default topology, some default SlimFly. We have some 2 endpoints which are talking to each other. We have and this is like the default topology. So they are using the default scheme, which uses 2 hops, right? This is the shortest path in SlimFly. And then what we propose is to divide these links into so-called layers, disjoint, like in subsets, which may be disjoint, maybe not. And they are called layers. And these layers are sparsified. So in each of these layers, we are grabbing some of the links and we are removing them from these topologies. Right? So we have layer 1, we have layer 2, and we may have more layers depending on our parameterization that we are going to speak a little bit in more detail later. What is important is that we're just replicating this routing pattern here, and we are just sparsifying it by removing these selected links. We can select these links using different schemes, and we have like a couple of schemes, but really the simplest one, which is also very powerful, is just random uniform samples. We just randomly remove the edges from these layers. And then what we are doing, we are dividing our flow into subflows, or maybe we are routing different flows using different layers, and we are just sending this data belonging to either different subflows or to different flows, depending on what we want to do, across different layers. And now the key insight is that as we are having these layers with not all of the links, because we remove these links, routing over these layers is going to use some path which is non-minimal, right? So within a single layer, we are routing minimally, but as the layer doesn't have all the links, globally speaking, it's going to be a non-minimal path. And then as we have different layers, we'll have different paths. So that's our key idea in the routing protocol. It works pretty well. So yes, these different layers enable multipathing, and what we did, we basically implemented this and developed this together with the transport protocols for Ethernet. Details are in the SC paper with lots of data, lots of evaluation. I'm going to skip that here because we don't have time. What is important is that SlimFly, again, assuming Ethernet, achieves higher net throughput at much lower latency than comparable cost factories that are built using the same amount of money. And now the next stage that we are going to answer is how can we use all these insights using the InfiniBand architecture, and how to actually do this in practice. So this Ethernet was actually done using simulations, different types of simulations, but now we really want to do this in practice on a real cluster. And here is also when Niels will come up and will grab the slides from me and will speak for the next couple of slides, because he was really driving this part himself in many aspects. So Niels, are you there?
Yes, can you stop sharing, please?
Yes, let me stop sharing now.
Okay. Let's see. Okay. Hello, everyone. I'll be covering the InfiniBand part. And let's stay with this idea of these layers and directly jump into the InfiniBand setting and understand how we can use this idea of this layered routing in the InfiniBand setting. And in order to understand how we can introduce these layers, we will quickly go over how addressing works in the InfiniBand setting, because it is a key component when thinking about multipathing. And in the InfiniBand setting, addresses are assigned to each node, and nodes are either switches or end nodes. And in the diagram on the left, you can see a very small SlimFly network with 18 nodes, and the black ellipses are the end nodes. And as you can already see, each of the ellipses has a unique identifier, and this identifier is called the LID. And this LID is assigned by the manager of the subnet and is used for destination-based routing, because in an InfiniBand setting, destination-based routing is used. Destination-based routing is very simple and very efficient for that reason, as it uses a single linear forwarding table in each switch that is indexed using the destination LID of a packet. So for instance, let's say we have end node 100 that wants to send to end node 200, and we have this path from switch 1 over switch 3 to switch 2. And how this switching will work is that switch 1 will index its forwarding table using the destination LID that is in the packet's header and determine the next hop, and thereby determining the output port that it will forward the packet on. And one limitation, so this is all very straightforward, but this has one limitation because destination-based routing gains a lot of efficiency by not making any changes to the packet and not modifying packets during transit. However, this also limits the multipathing capabilities. And in order to address this, InfiniBand, what InfiniBand has, is called LID masking. And LID masking works as follows. By masking a certain number of bits, we assign multiple addresses to each end node. So for instance, in the setting on the left, the end node that before was addressed using the LID 100 is also assigned the second LID 101. And also the same goes for the end node behind switch 2. And that way, what we can do is we can, in this forwarding table of the switch, we can enter a second entry for the second LID that is assigned to the same end node, but use a different next hop, and thereby use a different path, and thereby achieving this desired multipathing. And this is exactly the mechanism we will use to implement these layers into InfiniBand, thereby creating a one-to-one mapping from layer to LID offset. And I mentioned that this is done using this LID mask control. And what you can do is you can mask up to 7 bits of this LID address. And the LID address in itself consists of 16 bits. So what you might think, in that case, 16 bits is not a lot, right? And the problem is by masking a certain number of bits, we reduce the number of end nodes that we can support in the system. Because, say, if we assign twice as many addresses per end node, we reduce the number of end nodes we can support by a factor of 2. And so the question is, how many layers can we actually support? And in order to answer this, we look at we take the SlimFly topology that we construct using switches with router radix or switch radix 40, and try to construct the largest SlimFly topology while satisfying full global bandwidth and also satisfying the number of layers, so assigning that many addresses to each end node. And what we can see is that for 1, 2, and 4 layers, we do not actually have to sacrifice any network size. The reason is that in that setting, the network size is actually not limited by the address space, but rather by the hardware. So by the 40 ports that we have available. And for that reason, it is very apparent that 4 layers we can always use 4 layers with any size of a network that is based on the SlimFly topology. Furthermore, we can also justify using 8 layers because we reduce the network size, the maximum network size, as to speak, by a factor of less than 20% instead of this factor of 2, which would be a reduction of 50% that we would imagine we have by increasing doubling the number of layers. So keeping this in mind, we still haven't answered the question of how many layers do we actually need, right? We have seen that we now can use 4 layers without actually having to decrease the network size. So how many layers do we actually need? And for that, we will look at the layer generation algorithm that we use in the InfiniBand setting. We have seen a very small example of how these layers can be generated by Maciej, but in the InfiniBand setting, we'll use a more elaborate approach. And it's actually still quite simple, as for every switch pair that we have, we try and find an almost minimal path for every layer, right? And we also keep the first layer minimal to ensure that we also have the minimal paths. As we have seen, we'll always have one minimal path, of course, but we most of the time only have a single one in SlimFly. So, and for that reason, we keep the layer 0 minimal. And for the other layers, we just actively insert almost minimal paths, so paths that are one hop longer, and insert these into the forwarding tables. So in this example, on the left, you see the minimal path from switch 1 to switch 2, and the respective entry in the forwarding table of switch 1. And for the second layer with index 1, we will find this almost minimal path that has 3 hops, and insert that into the forwarding table as well, using this second assigned address that we have. So 201 instead of 200. And that's all there is to it, to the algorithm, to the essence of the layer creation. And intuitively, one would think now 4 layers should be sufficient, correct? Because we can always only use powers of 2 because we use this masking of bits in the address. So 4 layers should be sufficient to achieve this goal of these 3 disjoint paths to avoid the flow collisions Maciej presented. And unfortunately, this is not quite the case, because in some instances, we do fail to insert an almost minimum path into a given layer for a given switch pair. And this scenario is quite easy to understand, as for instance, imagine on the left, we have this the same topology network as before. We have already inserted this almost minimal path from switch 1 to switch 2, right? And for that reason, the switch 5, this one over here, has in its forwarding table the entry, the next hop 2 for the destination LID 201, right? As it will switch, it will send any packet with the destination address 201 to switch 2. Now the problem is, if we try and find an almost minimal path for the switch pair 5.2, we cannot insert that path in this layer because we already fixed the next hop, right? We have to route in this layer, we are forced to route minimally in order to satisfy the almost minimum path that we inserted earlier. For that reason, we will not be able to insert an almost minimum path and have to rely on there being almost minimal paths, disjoint paths in the other layers. So that's why we will need more than 4 layers. And as we can see from this figure, which I'll explain in more detail in a second, 8 layers, so doubling again, which was also still justifiable by not decreasing the network size too much, actually solves, as an overview, that more than 88% of switch pairs achieve at least 3 disjoint paths, which is our goal, right? This figure shows on the left we have 4 layers and on the right 8 layers, and the x-axis shows the number of disjoint paths for each switch pair. And on the y-axis, we see the percentage of switch pairs that have that number of disjoint paths. And as we see on the 8-layer plot, that's indicated by the red bars, we have less than 12% of switch pairs experience less than 3 disjoint paths. And using that configuration, we did some extensive analysis. We already can conquer a lot of can conquer adversarial traffic patterns. And at this point, Maciej will take over and introduce, talk about our further efforts.
Yes. So just to wrap up, because we also have not really much time left, but this will be like only maybe 2 minutes. So, as Niels mentioned, there are like many challenges in implementing this routing approach we had in InfiniBand, mostly because we had these constraints coming from InfiniBand. For example, not enough resources in forwarding tables because of the destination-based routing used in InfiniBand. So we had to do all these tricks. But the cool thing is that we were able to implement all these things in our test bed that we had. So for implementation of this thing and for the correctness debugging, we used a small test bed with 8 switches and then 16 nodes. We implement the whole approach using all these insights about number of paths, layering in the OpenSM, which is like the way we are doing switching in InfiniBand. And then we use this already to do some evaluation, some preliminary evaluation. So what we used this small test bed to make sure that this is actually correct, that all our schemes are not having any deadlocks, any issues, etc. We already were able to run the Graph 500 benchmark, the established benchmark for data-intensive communication workloads for some input, quite seriously large graphs. Okay, maybe not too large, but some initial graphs that we are testing. And on this plot, you can see on the x-axis, we are using different graphs. So edge factor is telling us how dense an input graph is. So the more of these, the larger the edge factor is, the more edges we have in the graph we are going to traverse. In the Graph 500 benchmark, the y-axis is showing the relative time compared to the baseline, which is using DF-SSSP routing, like the baseline routing in InfiniBand. We can see we have some quite variance in performance. But again, this plot is not destined to show you the performance insights. It's really shown to show that we actually have running routing protocol in InfiniBand working well. And now the question is, we want to get more performance. And for this, we actually constructed a medium-sized SlimFly that was driven in the last weeks and months. We used this for the SlimFly. We used 50 switches, 200 servers, and we did the construction at the CSCS. As you can see in the photos, it was a lot of work, of manual work in sorting cables that Niels was driving together with Hussein and with the people from CSCS. We are really grateful for this opportunity. And now what we are going to do, we are now preparing ourselves to run a set of large scale benchmarks that are kind of representing important modern high performance things that we are caring about, like deep learning, training, inference, weather forecasting, simulations, or data intensive communications like graph traversals, and collaboration with CSCS. And with this slide, I'd like to thank you all for your attention, to CSCS for their warm support, and we'll be open to any questions you may have.
Great. Thank you, Maciej and Niels, for the presentation. I currently don't have any questions in the queue, so I send it over to Hussein.
Okay, so fair enough. You mentioned some of them, the scientific applications that you would like to run. I mean, did you manage to run something so far, or this is something for the plans? Because so far until now, I can see some synthetic benchmarks, and it would be great to see some application that it is network hungry or latency hungry, where we can see direct benefits there. Is there?
Yes. I mean, yes. So we did run the Graph 500 benchmark, but not yet on the large scale, on the large cluster. Right?
Okay.
So this we extensively like tested on the small test bed, the Graph 500, and we have lots of data. And the cool thing is that we actually show some speed ups there, even though the small testbed is very, very highly unoptimal for this type of routing we have, right? So the small testbed was like a fully connected, very small, fully connected click, basically. And this means that you don't really have any benefits from multipathing there. You actually even are hurt by using multipathing in the setting. And we still got some performance improvements. So now we are like looking forward to, like, we are in the final phase of actually wrapping up the setting and the environment to run this thing on the larger cluster. And here we are going exactly to use this network hungry things, right? So Graph 500 is very hungry thing. You have lots of like very direct remote accesses into your remote nodes in the network to access like remote vertices in the graph. The same comes, for example, for training or inference of graph neural networks. So all these things are basically, we are going to use all of the things which are very, very network hungry, but also just to also compare wide spectrum, also some which are maybe not that hungry, like some stencils which are going to be less network hungry, also to see if we get any performance improvements for that type of stuff.
Yeah. Now the size we talked about 50 switches and 200 nodes.
Yes.
Now for the next step, do you think growing with end node, it just could bring some more benefit for your testing, or
Yes.
maybe number of switches?
Both will help, right? So both will help. Like with the SlimFly topologies, like the cool thing is that the larger you get, I would say the more advantages you are getting, because you are scaling the topology, but you are fixing your diameter, right? So you are basically preserving all your performance properties, but you are still getting a larger network. And that's why, like with the larger size, we could get even more performance improvements. So on one hand, if we just increase the number of nodes, like servers on this particular construction, this will also help, because then we can accommodate larger workloads, like for example, have larger inputs to our workload, because we have like 50 switches more and more threads doing something on this workload. At the same time, we don't really have to increase number of switches just by adding like 50 switches, if we add only 50 servers, then we don't have to modify any of the switches, because we can still nicely accommodate that many servers for using 50 switches. Exactly. But then if we have more switches, that will be even better, but yeah, then we need more switches, right?
I mean, the last point here could be just also a real comparison for this such size of a cluster with a different topology. So after finalizing the testing on SlimFly, recabling everything and building like a battery, that will make a lot of sense to rerun the entire tests and see what we can get. Yeah.
Yes, that's exactly the goal, to compare this to full bandwidth battery and see how better we are.
Yeah, thank you.
Okay, thanks a lot.
We do have one more question, and it comes from Benson. Yes, can one integrate adaptive routing into a job scheduler or in a cloud allocation request?
I mean, I would imagine that you could easily incorporate what we did into some job scheduler, because, I mean, okay, so the question is, can you impact the routing itself through the scheduler? I'm not sure. This would probably depend on a specific design, but what we could easily do, we could easily use our insights from especially the FatPaths paper, so the paper that analyzes in detail the technology agnostic routing in these topologies. There you can use our insights about about what mappings for what workloads are giving you better communication or like more bandwidth for different workloads, right? Because now, as you saw, depending on how you map these communicating pairs of endpoints to your topology, you will get fewer or less flow collisions, for example, or flow conflicts. There are like even more crazy effects. And now we could use these insights and then basically program your scheduling policies to get more performance.
Great, thank you.